Up to this point, if I asked you to take the antiderivative of 1 over x squared with relation to x, you would be able to do that by undoing the power rule. And that's pretty straightforward. However, we are, at this point, still unable to solve this problem, the antiderivative of 1 over x with relation to x. If we try to think of this with our power rule, this is like x to the negative 1 power, and if you increase this in by 1, you end up with x to the power of 0, which is 1, and obviously we're stuck because the derivative of 1 is not 1 over x, so this does not work. So in this video, we're going to answer the question of what is the antiderivative of 1 over x. And to do this, we are going to start with looking at the derivative of the natural log of x. My goal right now is to find y prime. If y is the natural log of x, what is y prime? So to proceed with this, I'm going to rewrite this equation as not natural log, but as log base e of x. The natural log, remember, is defined as the logarithm with base e, and I'm going to differentiate this function. Now the problem with this is that before I actually do this, if I just start thinking through what's going to have to happen here, there's going to come a moment where I'm going to have to take the derivative of log base e of x. And I obviously don't know what the derivative of that is. That's what I'm trying to find. So I can't just take the derivative of this thing with respect to x. So to get me out of this jam, I am going to rewrite this equation so that it's not in logarithmic form, but rather in exponential form. So we're going to write this as e to the power of y. Y was the old output, now it's my new input, and it's going to equal x. So e to the power of y is equal to x is the equivalent statement to saying that y is equal to log base e of x. And at this point, we can take the derivative, because earlier today, just as a quick reminder, or if you weren't in class, if you didn't hear this part, we talked about the fact that there is a function out there, the only function, such that when you take the derivative of it, it equals itself. And that is the function e to the power of x. It's a really important function. It's sort of like a differentiation identity. It's the only thing that you can take the derivative of and get itself. Much like when you multiply by 1, you get the same thing, or when you add 0, you get the same thing. When you take the derivative of e to the power of x, you get e to the power of x. So that's going to help us here, because we now see that we have e to the power of not x, but we still have e to the power of some thing. So let's try to think about what it would take for us to take the derivative of e to the power of y. Because I've got a different inside function than the variable that I'm trying to respect, I'm going to have to use the chain rule and think of this in this way. I'm going to take the derivative of the outside, evaluated at the inside, where y is my inside function. I'm doing the chain rule here. The derivative of the outside, evaluated at the inside, times the derivative of what's inside. Now y is my inside function, so the derivative of y is dy over dx. So this is my chain rule applied. The derivative of the outside, evaluated at the inside, times the derivative of what's inside. And this is all going to equal the derivative of x, which we know is dx over dx, which I'm just going to call 1. Now my goal here was to find y prime, which is dy over dx, and that is this piece right here. So to get dy over dx by itself, I simply have to divide each side by 1 over e to the power of y. I'm going to move over here now and rewrite this as dy over dx is equal to 1 over e to the power of y. And this is all good, but the problem with this is that my function that I've differentiated with, I've tried to differentiate my function with respect to x, but now I'm defining my answer in terms of y, which is no good. So let's see what we can do about that. And this becomes a pretty easy fix, because what we see is that e to the power of y, as it were, is the same as x. this convenient bit of information is going to come back into play here. So what I'm saying is that dy over dx is actually just equal to 1 over x. So in summary, we're using this knowledge that if my function is e to the power of x, the derivative is e to the power of x. And then if my function is the natural log of x, this is the one that we just figured out, the derivative is equal to 1 over x. And we can make equivalent integration statements using this information. The integral of e to the x is equal to e to the x plus c. And the integral of 1 over x dx, now we know, is equal to the thing that we can take the derivative of and get 1 over x is the natural log of x, which is great. So let's apply this just really briefly. If I say find the derivative of 4 times the natural log of 3x, let's see what would be required in order to take the derivative of this statement, 4 times the natural log of 3x. Well, 4 is a constant, so technically, even though I have a product rule situation here, remember the rule that says that I can drop my constant down and then just take the derivative of this function. So because I have an inside function, I've got to apply the chain rule. The derivative of the outside is going to be 1 over x, where x now is 3x, 1 over the inside function, so the derivative of the outside evaluated at the inside, times the derivative of what's inside, and the derivative of 3x is equal to 3. So I end up here with 4 times 1 times 3, which is 12, divided by 3x, or in other words, 4 over x.